Hi, everybody. Hope you're doing okay and you're safe. We're going to continue on now with Chapter 9. We just finished 9.2 with the quotient rule of radicals. And we're going to stay with that quotient rule of radicals for just primarily one more item. This item, however, is not going to be found in 9.3 nor 9.4. It's going to be found in 9.5, and we're going to take a look at it now because it is related to dividing with radicals. And the skill that we're going to be taking a look at is entitled Rationalizing the Denominator. So we're going to come up here and we're going to take a look at this statement again, this setup. This was the initial quotient rule of radical formation that we looked at. The nth root of A divided by the nth root of B. And rule number 4 mentioned to us that we cannot have a radical in the denominator position. And so we made use of the quotient rule of radicals to get away from breaking that rule. And for the ones that we did in 9.2, we were able to rewrite this, and we were able then to not have a radical in the denominator position. But we're going to come to another situation in 9.5 that is not going to allow us to do that. We're going to take a look at problem number 1 right here. I know I've already mentioned rationalizing the denominator, but I want to lead up to this phrase by taking a look at this example. This says 7 times the radical of 3 divided by the radical of 5. It's a problem that is structured in the same way as this format is here, where we are dividing radicals. So let's just try to do something with this based on what we've already talked about. This expression is equal to 7 multiplied by the radical of 3 over 5. That's what the quotient rule of radical tells us. But let's look at this new statement that we just created. We can't have a fraction in the radicand. So by using the quotient rule to this expression and changing it to its equivalent form, we're not gaining anything, because 3/5 cannot be eliminated. 3 isn't evenly divisible by 5. We have a fraction there that's going to remain, and we can't have that, because we cannot have a fraction as a radicand. And so we're going to have to come back to this original problem. We're going to have to take a look at a brand new skill. And that brand new skill is called rationalizing the denominator. And here's what this is about. Look at this denominator right here. It contains a radical. We can't have a radical down there. So we're going to have to get rid of it. This radical that's in the denominator position represents an irrational number. Yes, so does E. But it's the denominator in question that is breaking the rule for us, not the numerator. This denominator represents an irrational number because the 5 is not a perfect square. So what we have to do with this denominator to prevent from breaking the rule of not having a radical in the denominator, we're going to have to institute a new skill. And that new skill is called rationalizing the denominator. And rationalizing the denominator is the key skill found in 9.5. So we have to jump from 9.2 to 9.5 to meet this objective and to take care of getting this denominator not to have a radical in it whatsoever. And so we're going to need to turn this denominator, we're going to need to turn it in to an equivalent denominator that will make it become rational and not irrational. All right, well, now to be able to change this irrational denominator into a rational denominator, we're going to have to make this radical of 5 become a radical that's going to have a radicand that will be a perfect square, because we're dealing with square root. And so we have the radical of 5 right here in this denominator. If I put a multiplication sign here, we can do anything that we really want to do in terms of multiplication with a fraction. I can multiply the numerator by anything just as long as I do the same thing with the denominator. And so here's what we want to do. Here's the original problem. We put a times sign here and we make another fraction bar. We have the radical of 5 as this denominator. If we multiply that denominator by another radical of 5, I have one factor of 5 here, and now I have a second factor of 5. I now have two factors of 5. If we multiply these two radicals together, we will get the radical of 25. And the radical of 25 represents a rational number, which will give us a final denominator of 5 when we find its square root. But whatever we do to the denominator, we have to do the same thing to the numerator, so we're going to have to multiply the numerator by that same radical of 5. So just back to this denominator again, so I'm not losing anybody, because I don't want to lose anybody. The radical of 5 right here is irrational. I have to make it become rational, and the only way that I can do that is if I turn this radical into a brand new radical that will represent a rational number. I have one factor of 5 right here. I need one more factor of 5, and we put it right here. So let's come down with one brand new fraction bar. And let's multiply the two numerators together, and we'll have 7 multiplied by the radical of 3 times 5, or 15. The bottom, if we multiply those two radicals together, we'll get the radical of 25. We have done the task of taking this original denominator and rationalizing it. We have now made it become a rational number. So we leave the numerator as it is, and the radical of 25 will become 5. And now let's just take a look at this overall answer and just see if there's any reducing that can be done. We can't do anything with the 7 and the 5. The radical of 15 does not contain any perfect square factors. We have simplified it, we have rationalized the denominator, and we are now not breaking any rules. Number 1. Let's go to number 2. There'll be a few of them that we'll look at because each one of these are all kind of tweaked a little bit differently, but all with the same procedure. We have 60. Here's the divided by. The radical of 20. we cannot have a radical in the denominator. And so to get rid of it, we're going to have to rationalize that denominator. Now we're dealing with square root again. So if you wanted to do this, you could. You have one radical of 20. If we were to multiply both the numerator and the denominator by a second radical of 20, then we will make that denominator become rational. But that's also going to make numbers a little bit bigger, a little bit larger. So here's the tweak on number 2. Before we go through the procedure of rationalizing, look at this radical that's in the denominator position and notice that within the radicand of 20, 20 contains a perfect square factor of 4. Nothing higher, but it does have a factor of 4. I'm not going to prime factor 20 for you to see that. We should be able to look at 20 and say 4 times 5 is 20 and 4 is a perfect square. You can't use 10 times 2, but we can use 4 and 5. And so we're going to start this off by this act. Bring down the 60. And now we're going to use the product rule of radicals to bust this guy up into this. The radical of 4 times the radical of 5. We will then have it down to 60 over, he's going to come out of its house, and we'll have 2 multiplied by the radical of 5. Now, before we rationalize this denominator, this radical of 5, notice this numerator of 60 and this little factor of 2 down below, we can reduce that. We're going to reduce that little puppy right now. So just kind of one little move moved into another. So I'm going to cancel this 2 out and make it a 1, and 2 will go into 60 30 times. So now let me elevate what we have up here. We have 30 over the radical of 5. We've got to eliminate him, because doing nothing, we're breaking a rule. So we're going to now multiply, and we're going to rationalize the denominator. We're dealing with square root. I have one radical of 5. If we multiply both the top and the bottom by a second radical of 5, times 5 will make it the radical of 25, which it will come then out of its house and give us a 5 in the denominator. Bring a line down. We have 30 times the radical of 5 on the top. And the radical of 5 times the radical of 5 will give us the radical of 25. We will then have 30 root 5 over 5. He comes out. We have rationalized that denominator. And then again, we can reduce this. 5 will go into both. Not him, but these two. 5 goes into itself once and into 36 times. And your final answer, if Kristen can get it right down here, will simply be 6 root 5. And that would take care of the problem. So it's a few steps. Yeah, it is. That's the process of rationalizing the denominator. Let's take a look at a third. Another appearance, maybe another look. There's the problem. can't have a fraction in the radicand. But that fraction can be reduced. And before you rewrite this problem, it would be to your advantage to look at the fraction and see if the fraction can be simplified. It can. 2 divides into both numerator and denominator. So we can pull this down. 2 goes into 2, 1. 2 goes into 54, 27 times. Now it's been reduced. And we still have a fraction in the radicand, and we can't have that. So now we're going to have to use the quotient rule of radicals and split this up so it becomes written in this form. So we'll have the radical of 1 divided by the radical of 27. The radical of 1 represents a rational number because the principal or positive square root of 1 is 1. So he's going to come out of his house. And if we look at the radical of 27, 27 contains a perfect square factor of 9. I don't think it's necessary to show the upside down division. 9 times 3 is 27, and 9 is a perfect square. So let's come down and put the fraction bar and simplify this numerator radical to 1. And let's split him up using the product rule. The radical of 9 times the radical of 3. We'll now get this down to 1 over 3 root 3. Now let me elevate him up here so we have a little bit of room. Now we've reached the point where we need to rationalize. You don't need to worry about touching him. He's the one that needs to be touched because he's the radical. We're dealing with square root. If we put a times sign and the fraction bar, I have the radical of 3. If we multiply this radical of 3 by another radical of 3, it will make it become rational. So we're going to multiply the denominator by a radical of 3. And what you do to the denominator, you got to do with the numerator. Numerator now, brand new one. 1 times him. Carefully the denominator. Bring him down. Now let's use the product rule of radicals that tells us when we're multiplying 2 radicals together, you multiply them together to get a single radical. The radical of 3 times the radical of 3 is the radical of 9. Then we have the radical of 3 on top, and on the bottom we have 3 times its root, which is 3. Answer, radical of 3 over 9. And don't do any reducing because the numerator is a radical and the denominator is just a plain ordinary real number. And they can't be tinkered with. They're done. That would be our given answer. Let's take a look at one other one before maybe we just pause for a bit. Just one more at this particular point. The radical of 11 over 15 times the radical of 3 over 2. Now we know we can't have fractions in a radicand, but it certainly doesn't mean that we can't multiply them together to get a single radical. And that's what we want to do. You should not be thinking of doing any rationalizing of any denominator yet. First of all, this is not in the form to rationalize, and neither is he. We want to multiply initially those two radicals together to get a single radical. We're going to be able to do a little cross-canceling on this one, so I'm just going to show the radical of 11/15 times 3 over 2. We can do a little cross-canceling here. That numerator of 3 with that denominator of 15. 3 will divide into itself once, and it'll divide into 15 5 times. We will get this now down to the single radical of 11 times 1, 11, over 5 times 2, 10. And now we've gotten it down to the radical of 11 over 10, a single radical. Well, we can't have that fraction as a radicand, so now we're going to have to take this, split it up into the red form. And that will now give us the radical of 11 over the radical of 10. We can't have a radical in the denominator. 10 does not contain any perfect square factors. 10 only has a 5 and a 2, and neither of those are squares. So we can go right into rationalizing that denominator right now. Put a times sign in the bar. I have one radical of 10. I need another 10. It takes 2 of a kind to make a perfect square. So we need another radical of 10 on the bottom, and we likewise do the same thing on the top. Come down with a bar. Multiply those two numerators together to get a single radical. 11 times 10 is 110. So we have the radical of 110 on the top. And on the bottom, the radical of 10 times the radical of 10 will give us the radical of 100. And you can see that that denominator now represents a rational number. And we will have as our answer the radical of 110 over the root of 100, which is 10. And that little puppy is done. And we have done the task of rationalizing the denominator. So we'll come back in a few moments and continue on with this and work with variables a little bit.